Have you ever wondered what happens when a star, millions of times larger than our sun, explodes? In the grand theater of the cosmos, stars are the lead actors, born from the cosmic dust and gas that fill up the universe. These celestial bodies live their lives by burning hydrogen, their primary fuel, in a process known as nuclear fusion. This fusion process generates heat and light, creating the glow we see from Earth. Over time, however, these stars exhaust their hydrogen reserves. Now imagine a star, much larger than our sun, reaching the end of its hydrogen fuel. No longer able to sustain its own weight, it collapses and then rebounds in a colossal explosion. This is what we call a supernova, a cosmic spectacle marking the end of a star's life. So a supernova is essentially the dramatic finale of a star's life. But what happens during this spectacular event? Picture this, a star nearing the end of its life starts to collapse under its own gravity. What follows next is an explosion of epic proportions. This is the anatomy of a supernova. It's a stellar spectacle like no other, where a star, having exhausted its nuclear fuel, can no longer hold back its own weight. This lack of fuel leads to a drop in pressure, and the outer layers of the star start to implode towards the core. But wait, there's more. The star's collapse is so rapid and so intense that it creates a shockwave. This shockwave, like a cosmic ripple, travels through the star, reaching its surface and triggering an explosion that throws the outer layers into space. This is the brilliant flash we see when we observe a supernova. A light so bright it can outshine an entire galaxy for a brief moment. However, not everything is blasted away. The core of the star remains. Now, depending on the mass of the original star, two things can happen. If the star was about 8 to 20 times the mass of our sun, the core would become a neutron star. This is an incredibly dense object, with a teaspoon of its matter weighing about 1 billion tons. On the other hand, if the star was more than 20 times the mass of the sun, the core's gravity would be so strong that not even light could escape it. This results in a black hole, a point in space where gravity is so intense that nothing, not even time, behaves normally. So as you can see, a supernova isn't just a star going out with a bang. It's a complex and fascinating process where stars transform, where matter is recycled, and where the building blocks of the universe are scattered across the cosmos. So a supernova is not just an explosion, it's a transformation, a rebirth of sorts. But what does this mean for the universe around it? Imagine an explosion so powerful it outshines an entire galaxy. That's a supernova for you. A supernova, quite literally, shakes the universe. When a star, having exhausted its nuclear fuel, collapses under its own gravity and explodes, it unleashes an unimaginable amount of energy. This cosmic detonation sends a shockwave rippling through space at speeds of up to 20,000 kilometers per second. Yes, you heard it right, 20,000 kilometers per second. But what does this mean for the universe around it? Well, the shockwave, like a cosmic battering ram, can trigger the formation of new stars. The dense clouds of gas and dust in space, often the nurseries for stars, are compressed by this shockwave. This compression can kickstart the process of star formation, causing these cosmic cradles to give birth to new stars, and perhaps even planets. And the impact of a supernova doesn't stop there. The explosion is so hot and so violent that it cooks up elements heavier than iron in the star's core. These heavy elements, along with the remnants of the star's core, are then blasted into space by the supernova. This stardust, rich in heavy elements, then drifts through the cosmos, eventually becoming part of other stars, planets, and even life itself. Quite fascinating, isn't it? The iron in your blood, the calcium in your bones, and the oxygen you breathe, all were once part of a star that met a spectacular end. So when you gaze up at the night sky, remember this: each star could be a future supernova, ready to sow the seeds of new celestial bodies. And each supernova, in its death, breathes life into the universe. So, a supernova is not just an end, it's a beginning, a catalyst for the creation of new celestial bodies. What remains after a star has given its final performance as a supernova? A question that has intrigued astronomers for centuries. Let's delve into the aftermath of a supernova, where the spectacle of a dying star leaves behind an array of cosmic wonders. When a star goes supernova, it doesn't just vanish into thin air. The core of the star, the heart of its being, survives the cataclysmic explosion. What happens to this core is truly fascinating. Depending on the mass of the original star, the core can transform into one of two celestial phenomena, a neutron star or a black hole. Imagine the core of a star, dense and hot, collapsing under its own gravity. If the core is less than about 3 times the mass of our Sun, it squeezes itself into a neutron star. Now, these aren't your run-of-the-mill stars. Neutron stars pack their mass into a sphere just a few miles across. They are so dense that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. These cosmic oddities spin incredibly fast, sending out beams of radiation that we can detect here on Earth. But what if the core is more massive, say more than 3 times the mass of the Sun? Well, the gravity is so strong that not even light can escape, and a black hole is born. These enigmatic entities warp space-time around them, their gravitational pull so strong that they devour anything that ventures too close. Yet the aftermath of a supernova is not confined to the star's core. The explosion hurls the outer layers of the star into space, creating a nebula. These nebulae are vast clouds of gas and dust lit up by the energy of the supernova. And within these nebulae, new stars and planets can form, born from the remnants of their supernova predecessor. So, even in death, a star continues to contribute to the universe, either as a neutron star, a black hole, or a nebula. In this grand cosmic theater, the final act of a star is simply the beginning of another celestial story. So why should we care about supernovae, these celestial fireworks, you may ask? Well, imagine a detective trying to solve a mystery without any clues. That's what studying the universe would be like without supernovae. These fantastic explosions are not just a spectacular light show. They are the universe's way of leaving breadcrumbs for us to follow. They provide clues about the life cycles of stars, the formation of galaxies, and the origins of elements. Each supernova is like a page torn from the biography of a star. It tells us how a star lived, what it was made of, and how it died. By observing these celestial events, we can understand the lifespan of stars, their behavior, and their ultimate destiny. But it doesn't stop there. Supernovae are also cosmic furnaces where elements heavier than iron are formed. You've probably heard of the Big Bang, right? Well, that event created only the lightest elements such as hydrogen and helium. The rest, everything from carbon to uranium, was synthesized in the hearts of stars and spread across the universe through supernovae. That's right, the iron in your blood, the calcium in your bones, even the gold in your jewelry, all came from the heart of a star that ended its life as a supernova. And finally, studying supernovae helps us understand the universe better. They are like cosmic lighthouses, their light reaching us from billions of light years away, allowing us to peer into the distant past. By observing them, we can measure the rate at which the universe is expanding, giving us insights into the nature of dark energy, one of the biggest mysteries in modern physics. So next time you look up at the night sky, remember, each star has a story to tell, a story that may end in a spectacular supernova.